So I talk on nano-engineering for energy storage. I'm Dr. Theo Suter. I'm a postdoc research associate or a postdoc at UCL. This means I'm basically a full-time employee of UCL. I started on the dark side and joined Imperial as an undergrad. I did chemistry of molecular physics, so very different to what you guys are probably applying for. Then went to do my PhD in sort of nano materials and chemistry in UCL. So I was in the chemistry department at UCL. And then about 2.5 years ago, I moved over to the chemical engineering department. Still working on nanomaterials, but for an application. I personally love the fact that now I work on something real. Before doing a bit more chemistry stuff, a bit more, didn't have a reason to it. It just kind of, you researched it and then you just moved on. You didn't, this is now has a point to it. Doing energy storage, to me, this is important. So this is the, this is the research group that I'm a part of. This is the Electrochemical Innovation Laboratory, or EIL. There's a lot of us. There's actually more than us in this picture. It's a big research group. Research groups aren't usually this big. Mostly what we focus on is electrochemical devices. So you're talking about stuff like batteries, fuel cells, electrolyzers. Way to use energy to create materials, or use convert energy. Mostly that's what we do. This car in the front, that's a hydrogen-powered car. And we're going to be talking more about these, but this is something the group has and we can drive around if we want to. So why are we doing this? Why are we, as the question asked for, why are we focused on energy storage? Well, because of this. This is a bar graph showing, or line graph showing the average temperature of the world over the last 170 years. Blue is below the average temperature and red is above the average temperature. And as you probably full well know, and as you can clearly see, the average temperature has increased dramatically over the last 20, 50 years. This is an issue. This isn't going away anytime soon unless we do something about it. So we really need to do something about it. And this is why energy storage is a part of the reason why we need to work on energy storage. As also one many you know, the reason this is happening is one of the reasons it's happening is generation of CO2 in the atmosphere. And what we can see looking at this graph, which tells us the energy consumption, how we consume our energy over the last 220 years, is most of the energy, we've been increasing the amount of energy we're doing. And that's mostly due to economic changes, but also population growth. But the energy sources are still mostly crude oil, coal, and natural gas, all fossil fuels, which is what's causing the CO2 generation, which is causing the heating of the global temperatures. Now, the other issue is these renewable sources, which are getting definitely more so in the future, are a small percentage of the overall energy generation. We need to make this most of it, and we need to do that pretty quickly. Otherwise, climate change is going to start to have some serious implications, and already is. The problem with renewable sources is, as you probably know, is that they're intermittent and not quite as reliable as we want them to be. And what a consequence of this, or also for this, is we don't consume energy in a linear fashion. This is a graph showing the energy consumption of a typical UK home over 24 hours. It's not the same amount of energy all day long. It changes over time. So you have the energy generation sources which are intermittent, and you have changing energy uses over a day. So the two just don't combine. The only way to combine them is to have energy storage. During the sunny times, during the high wind times, you store your energy, and then you use it when you need it later. The only way renewable energy systems work is with energy storage. So there are a few interesting ways of doing energy storage. One of the main ones we're looking at is batteries. So, for example, Tesla's large mega battery farm in Australia, that's a good example of that, storing electrical energy, the backup energy, as in batteries. Another solution to this is fuel cells. Now, this doesn't look like anything, but fuel cells are a way of storing energy, and we're going to get more of that into a bit. So, first of all, I work on fuel cells, so I don't work on batteries. I'm a bit biased on which one's better, but at the end of the day, we're never in the future, we're going to use both. We're going to have battery cars and we're going to have fuel cell cars. This is what's going to happen, because they're good for different things. They have different reasons that make them better, because they're very different chemistries that are going on. So you're going to have both existing in the future at the same time. So I focus on fuel cells. So quickly about batteries. Most batteries at the moment are made of lithium and cobalt. Both are very rare materials in the Earth's crust, and it's fairly, at this point, unfeasible to make every car and every energy storage system out of lithium and cobalt. It just isn't enough. It's going to get way too expensive to try to do that. One of the other problems in batteries is safety. This is a video of our lab. This happened in our lab. Of what happens if you take, it's going to be a little bit loud. If you put your headphones really loud, turn down a little bit. Of what happens if you put a nail through a charged battery. It explodes. And that was only a half-charged battery. So if you charge it more, it's going to set fire more. There are issues with battery technologies, but they are being worked on by other people. I'm a fuel cell guy. So what are fuel cells? Fuel cells, when we talk about fuel cells, we start talking about something called the hydrogen economy. Because fuel cells use hydrogen to generate power. So when we talk about fuel cells, we need to talk about hydrogen economy. Hydrogen economy is essentially this idea. You have your renewable solar and wind farm. And when you generate them into you generate electricity. So they go into the national grid, they use, but you have excess electricity. You can store that excess electricity in batteries and then put it back into the electrical grid. Or what you can do is something a bit different, which you can use electrical energy and generate hydrogen. You can actually use electricity using electrolyzer, generate hydrogen gas and store this hydrogen gas, store the hydrogen gas. Then this hydrogen gas can be used for applications such as fertilizers or metal, like more industrial stuff, or you can use it to power hydrogen-powered vehicles, like the picture of the car we saw earlier. But then in the times when you need it, you can then convert this, hydrogen back into power via the hydrogen power generation. You can use the hydrogen power generation. The way we do this is something called a fuel cell. Also, the hydrogen cars use fuel cells. So the physical machine that lets us do this and this transition, converting the power into end electrical, is something that's being worked on. So hydrogen cars, they're here, as I say, they already exist. Hyundai, Toyota, and Honda all have hydrogen cars. There are hydrogen storage centers all over Europe. Hydrogen fueling stations all over Europe. There are not very many of them, but they are growing to be more. Hydrogen fueling has a benefit such as over battery cars, such as if you're refueling a hydrogen car, you roll up to a petrol station, you fill it up, it takes 2 minutes and you drive away. It's the same basically as a petrol car. The infrastructure is very similar. It's very different to batteries, which take a long time to recharge. I mean, they're typically done, you could do them at home, but again, it takes a long charge. So again, differences in the way the technology works. So this is definitely something that's real, it's commercial, but it needs to be more so. If we're going to make a big change on the world, everyone's got to be driving hydrogen or battery cars. So how do fuel cells work? As I say, fuel cells use energy, and they use the energy between the conversion of oxygen and hydrogen into water. Now, you can see there's energy in this reaction, because if you take a balloon of hydrogen gas and you set it on fire in air, so with excess oxygen, it will explode. This is energy being released. There's energy being released uncontrollably. This is very hard to control, this energy. So you could, for example, do what you do in like a coal-fired power plant or an oil power plant, where you use the heat from those explosions to heat steam, to make steam, which would turn turbines, generate power that way. But we're not going to do that. We're going to do a much cleverer way of doing it. But we're going to do the same reaction. So what we're going to do is something called a fuel cell. Now, it's actually quite simple, even this diagram looks a bit complicated. We put our fuel in. That fuel is the hydrogen gas that we had before. Now, this hydrogen gas goes onto this this grey layer, which we're going to call a catalyst layer. And on this catalyst layer, or a anode, because electrochemical system, so it's, we call it officially an anode. In this catalyst layer, the hydrogen gets separated into its H+. I call H+ protons. It's just something I've got used to, because they're actually just protons, so they don't have an electron. H+ and the electrons. So this separates into the H+ and the electrons, and they both independently make their way to this side, which is the cathode. This is another catalyst layer. On the cathode, the electrons, the hydrogen plus, and the oxygen all react together to form water. So on this side, we have the hydrogen being split into the H+ and 2 electrons, and we're using those electrons in that H+ with the oxygen to form water. This is the same reaction that occurred in the explosion video, but it's happening on 2 separate catalyst layers and being transferred between them. So it's a lot more controllable and therefore a lot safer. We can also control how much fuel we put in, so we control how fast we want the reaction to happen. This system is very much cleverer than just exploding it. The other benefit about the system is when we generate these electrons pass through an external circuit. This is the power generation. We are directly creating electrons that are being used to generate power, which makes these fuel cell systems very efficient. So how do these work? I've been talking about these catalyst layers, but how do these actually work? So some of you would have done catalysis or sort of ideas in A-levels. Basically, you will have a metal catalyst, in this case platinum, and it has to be on a carbon support, a carbon or conductive support at least, normally carbon. And so this is our reaction, which is happening on the cathode side, that right-hand side. So what's going to happen is our oxygen will cut to the surface and attach onto the surface, followed by those H+, and then followed by the electrons. And once they're all combined on the same place in the catalyst surface, they form the water molecule, which then just goes off, does its own thing. That reaction step generates the energy. So you could already see that for this reaction to occur, every single one of these components has to get in contact with this platinum surface. If they can't get in contact with the platinum surface, they aren't going to react. So if we have a situation like this on the right, where we say it's broken off, this bit of platinum isn't connected to the electrical network of the fuel cell, what will happen is our gases will come in, our H+ will come in, and our electrons that won't be able to, so they're trapped. And so this reaction will never complete. What this means is that if you have a car and you have a platinum carbon fuel cell car, you're paying for platinum in that car that is not being used. So that's not only weighing your car down, but you're paying for something you're not using, and it's platinum, so it's going to be expensive. And that's not efficient, and that's not cheap, so people are not going to buy it. Other examples of this is if you have a system where you have trapped platinum. So the carbon surrounds it in a way that the gases and the H+ just can't get to it. In that case, your electrons can, but because you have no gases for it to react with, you can't. So what we're saying here is the structure of the morphology and structure of the way you've deposited your carbon and your platinum has a huge impact on the way your fuel cell performs, and that changes the way your car performs and how cheap your car is, how fast it goes, how efficient it is, all these factors. So what I do is we look at the nanoscale engineering of these systems. I think these platinum particles are 2 to 5 nanometers big. So we're talking tiny, tiny scales, and how this affects the big scale of the car. So I've written carbon here, and I mean, you know, there's different forms of carbon. One of the most common forms of carbon that is used for commercial fuel cell vehicles is something called carbon black. They're these kind of spheres of about 50 nanometers across. And if you imagine a ball pit full of spheres, there's air, when you put them all in, there's air between them, there's gaps between them. And this is good because this is what allows the oxygen through. And the carbon black is also very cheap, so obviously companies like making stuff out of it. The problem with it though, it doesn't last very long. It's the chemical structure of it is not as durable. So what we want to do is have a similar material, but more durable. So this is one of the things I do is I work with graphene. Now, I mean, you've heard of graphene. I'm not going to go fully into everything about it because there's a lot of stuff about it. If you're interested, read up about graphene. Graphene is a very different structure. You have these long sheets, so it's very, very thin sheets, but they're very long. They have very high they can have very high electrical conductivity. They can be made to form very high surface area. So there's lots and lots of space between them. But most importantly, for what I'm interested in, they have a very different chemical structure, which makes them much more durable and will last a lot longer in a fuel cell. So if you have a car which has graphene in it, you could make it last 2 to 3 times as long, potentially. So important people will much more like to buy a car that lasts 2 to 3 times as long before you have to buy a new engine. So this image is actually what one of these catalyst layers looks like. Now, probably not seeing don't know what this looks like. So this, a kind of white bit up here is a catalyst layer. This is 10 microns thick. 10 microns is the diameter of a red blood cell, roughly. So that is a 1 red blood cell thick. So that's kind of the scale we're looking at. It's tiny, but we've got to engineer these things. So a quick overview, the bright dots, they're the catalysts, they're the denser metal. The kind of less bright gray areas, like around here, this is the carbon, those spheres of carbon black that we saw. And these kind of like black areas, they're where there's nothing, they're just empty. So this structure it's all intermixed. It's like a good cake batter. It's all catalyst and support and some holes in between. It's all very intermixed, and so it works quite effectively. But we want to make it better. We want to change it to graphene. So we're going to make one out of graphene. And this is a similar image of that structure made out of graphene. Now, again, the bright dots, platinum catalyst. These kind of gray areas, they're the graphene. You can even see the way it flakes. If you look at one like here, you can see the way that this particular one is a single flake. They kind of stack up as the issue. So those of you looking at this and look says this looks like a mess, you're right. It is a mess because it's not very good. All of this catalyst is all trapped together. How is the oxygen meant to get in there? It can't, basically. It's all trapped. So we're paying for this platinum that we're not using. And so the electrode amount of this performs really badly. It doesn't generate much power, so it's not very good. And that's because of those examples we saw earlier where we're trapping the platinum and we're not actually using it. That's really bad. So one of the things that I worked on, or I do work on, is ways to make the platinum electrode deposit in a way that we can control and that utilizes all of the platinum. So this is kind of a cartoon of what our one looks like at the moment on left here. It's not very good. You can't really get the H plus of the oxygen in there. It's just all trapped. It's very dense. So what we want to do, and what we do is we spray our own electrodes. So this is my large robotic spraying system. And we program this thing to, it has an ink that comes all the way around here, and then we put it in on the side bit over here. We control this to spray how much we want, how fast we want it, the area. It's a lovely machine. So we use this, and what we can do is we can change the way that this thing deposits it by putting in extra bits into it. In particular, we call them additives. And so what this means is when we deposit the graphene, we deposit it with these big blobs in between. And then we can just remove them because I chose the right additives to put in so that we can easily remove them. And now the oxygen and the protons H plus get in. So by doing a simple manufacturing step to our spraying system there, we can actually change the electrode structure, which should increase performance. So this is our picture of it beforehand. As you see, it's very, very dense, not much space between all the catalysts. And after we've done this treatment, what we can see is quite a large difference. Now, obviously, like down here, you have these graphene layers and you have the platinum on top. There's a lot more space between the layers. So this is where your oxygen is going to get through. So we're going to utilize it a bit more. You have these layers in here. You have a lot more space. Obviously, it's not perfect. There is still a lot of catalyst over here and maybe over here, which is not being used. But we see a big improvement just by the simple addition of this this additive into the way we make the electrodes. And it's that simple manufacturing systems that I really look at and I investigate to see how we can make these electrodes much better. And so when I will make them and I will test them, and what we're seeing is a big improvement in the performance of these graphene-based ones. And when we are recent testing on the graphene has shown that it is in fact a lot more durable than the carbon black. So we are making more durable fuel cells. I mean, we got some way to go to make them the same performance as the commercial ones. They're not quite up to standard. They're close, but not quite up to standard. We've got some more work to do. We need to use all this platinum and this platinum up here, but we're along the way. So that's pretty much what I do. This is my group again. So thank you for listening. I've got some questions here that I will go through. So the first question I got is, how does the proportion work in terms of making the catalyst? How do you mix platinum, graphene, carbon black to ensure uniform throughout the catalyst? So depending on the way you're manufacturing it, you're going to have a different proportions and a different way you mix it. Generally, of our spray system, we will have what we call an ink. So we'll take the physical, sorry, not physical, the powder of the carbon black or the graphene and the platinum, mix them together in a liquid, typically a mix of different solvents, because this way which solvents you use and what temperature you evaporate them at changes the way the catalyst layer forms, in the same way that graphene versus carbon black does. So you can change the thickness and change the spacing. So we'll mix all the components into an ink, and then we will sonicate the ink together. So sonicating is mixing, but you're using a sonic probe to give everything a lot more motion. So everything mixes a lot quicker in these systems. You can look up sonic baths or anything if you've never heard of them. Sonic baths or sonic probes are one to look up. There's probably videos on YouTube, and we mostly use them. Cool, next question. Even if electron doesn't attach to the H plus in the oxygen, didn't it pass through the electrical generator and produce electrical current? There's no potential for it to do so. There's no there's no current gain from it doing so. There's no reason for it to do so. So because there's no reaction to do so. So the oxygen can deposit on the surface and the protons can deposit on the surface. But you're talking about one physical reaction. And those catalysts are generating thousands of reactions per second. So if that one electron might be ready to go round and be around, but he's not doing anything. So it's not that you don't get the initial, you're supposed to get the initial electron. That very well might happen, but it's completely inconsequential because you want that thing to thousands and millions of reactions, not one. I hope that answers that question. Next question. How recyclable are catalysts there since platinum is expensive and rare? Very good point. So platinum being expensive is an issue, though catalytic converters in normal cars typically would have about 3 grams of catalyst. The current catalyst in this fuel cell car in the picture in the background here has about 20 grams. The next generation of these ones will have 10 grams. So you're talking about having 3 times as much platinum in this car, this fuel cell car, than you have in a normal car. So you're not talking a huge amount more. Everyone working in this area is trying to bring it down. That's one of the main goals of people working in this area, is try to bring that amount of platinum UC down. But you're right, you are going to need to recycle these materials. Platinum is a very strong material, so it is possible to, for example, burn away the rest of the material. You can just take the rest of the fuel cell, burn it, and be left with platinum, because the platinum is very strong, very stable, it's not really going to do anything. But the actual recyclability of these catalyst layers is a big issue and is being looked at by lots of scientists around the world. So you're right, it is something that needs to be worked on. Okay, so I got another question. Apart from fuel cells, how do you think carbon capture and storage will develop in the future to help the problem of climate change? Well, I hope it will develop a lot. We really need it, to be honest. The energy storage, as I say, is not going to just be fuel cells. Fuel cells are probably part of that system, part of that equation. Batteries are also going to be part of that system. Carbon capture, and the energy storage system is the future, right? We're going to need this to combine with the renewable power to have the future. That's how we're going to generate energy in the future. The carbon capture, in my opinion, is probably something that's going to undo a lot of the damage that's done already. Now, if you have a combination of, for example, oil power plant and carbon capture, that could work, but you're going to need all of these things together if we're really going to turn back climate change. So this is quite a good question. So can't we use other reagents other than hydrogen and oxygen with higher difference in electrical potential to decrease efficiency of the cells? The short answer is yes, we can. There are many types of fuel cells that use different reactions. The reason we pick hydrogen is because of simplicity. If you pick some, you can, for example, do direct urea, direct methanol, direct ethanol fuel cells. You can make it also all sorts of stuff. You can do direct carbon fuel cells. The reason we choose hydrogen is because hydrogen and oxygen make water. That's great. You don't have to worry about any byproducts. Literally all they can make. That's all you got to worry about, making water. Making water is absolutely fine. And as part of the hydrogen economy, we can use this spare electrical power from the renewable energy systems to turn water back into hydrogen. So we have this closed system. We have this closed loop where we take energy mostly from renewable systems, so basically the sun, mostly, and then use that to generate oxygen from water, oxygen and hydrogen from water, and then we react the oxygen and hydrogen back into water. So we have this closed system, and it's this closed system that's the renewable bit, because it's completely closed. There's no loss, there's no gain, there's no other gain that we don't need. That's basically why oxygen and hydrogen are one of the preferred systems. But you're right, other systems do exist, and they typically might have higher efficiencies. Question, another good one. Is it possible to place platinum with other metals? Are there any alternatives? Yes, is the short answer. There are a few different many different people working fuel cell technologies. Some of the people work on engineering systems, so they don't care about what catalyst you have, they care about how efficient you can make the engine run. So you're talking like what you could consider a fully engineering a car factory. There are people like me who work in between. I have some different materials, but I play with the structures of the electrodes. And I'm kind of between the chemistry, chemical engineering. But there are people, especially in the chemistry departments, who look at other catalysts that can be used instead of platinum. As you're right, it could be cheaper, it could be a lot better. That is a big ongoing area of research. Now, there are lots of alternatives to platinum. There are lots of alternatives to platinum, such as you get a lot of transition metals. You get iron, cobalt, stuff like this, but they have a lot of issues. Most issues is they're really not as good as platinum. Platinum is just very good at what it does. And the other issue is it's not very stable. Platinum is very stable. So you put platinum in a fuel cell, it'll be there for a long time. It's not going to change into anything. You put an iron-based catalyst in there, it's going to turn to iron oxide, so it's going to rust and just leave the catalyst. So it's being worked on a lot. It's a lot of research on that, but it's not as good as platinum. In the future, there might be other non-platinum alternatives. We'll have to see. So yes, again, another good question. So if my understanding is correct, hydrogen is currently mass produced by steam reformation like hydrocarbons, and would the hydrogen process other gases that would potentially harm the platinum? Yes. So at the moment, hydrogen gas is made by something called steam reformation. And steam reformation is basically you're using fossil fuels. So this isn't renewable. No hydrogen used at the moment is renewable. When I talked about a technology called electrolyzers that converts water into oxygen hydrogen, that is something else that is being researched. It works, it fundamentally works, but people, again, like fuel cells, trying to make it work better, trying to make it cheaper. So as part of this hydrogen economy, not only do we need to make fuel cells very good, we need to make electrolyzers very good. If you can make electrolyzers, then you don't have to worry about these other harmful products that might exist in steam reformation. And really, if you're doing steam reformation, you're not having a renewable energy system. You need to do it by electrolyzers, basically. So, next question. Using hydrogen in a high temperature pan risky due to combustible nature, how do you overcome the safety issues from having to trade efficiency? So, it is risky. It is, as we talked about, as we showed the battery systems, battery set on fire if you damage them. Hydrogen gas is a gas and explosive in air. Petrol sets on fire and can explode when in fuel tanks. The nature of cars is that energy storage creates energy, and if you release energy in an uncontrollable way, it causes an explosion, and therefore intrinsically unsafe. All energy is. A lot of effort has been gone into hydrogen storage safety. The hydrogen tanks they use are like ridiculously thick steel, and they're very strong. But obviously there is still safety issues. In the same way that people say you shouldn't smoke at petrol stations, there's safety issues with the fumes of petrol. All of this technology has risks. And I say there is a lot of safety stuff about it that's going on. Yeah, that's all I can say. If you, I'm not as, the industrial safety stuff is something that I'm not as much of an expert on. So sorry about that. Next question, is water releases water vapor? So in that reaction, you had the oxygen and the hydrogen reacting to form water. So we would have liquid water forming, but in the fuel cells, they're typically run between normally 70 and 90 degrees. There's different type of fuel cells that run at about 120 to 170 degrees. So you're talking near the boiling point of water. So you get a weird intermix between the liquid phase and the vapor phase. So the initial reaction will probably produce a water, and you have localized water around the platinum, which is, you guys don't need to worry about something that is an issue in fuel cell technology. You get these water build up that has problems for mass transport of gases, and yeah, it's an issue. But mostly this water is removed as a water vapor because the fuel cell is running at 70 or 80 degrees. So that water, some of the water heats up and will vaporize and be carried out by the continuous flow of air, because these fuel cells have a continuous flow of reactants through them. So you're running air through your cathode. So as the air comes through, it dehydrates the catalyst layer. So a mixture of water, it usually gets moved with water vapor, but it's created as liquid water. if that answers. How safe is fuel cells since hydrogen is highly flammable? Again, similar question. Degradation can be an issue. If you degrade your fuel cells, you can get situations where the hydrogen and oxygen directly react. But that is like worst case scenario, and any good system will have safety protocols to stop that from happening. You can, when you test one of these, you can tell that that's happening way before it ever gets dangerous. The storage of hydrogen in the car, and if it crashes with another car and then maybe releases gas, again, that's a lot of work being done on that, but it mostly comes down to not having that much, like having very, very thick hydrogen canisters, and just, yeah, that's all the safety stuff. But the fuel cells themselves are fairly safe to run, because you're not going to be having any direct contact between the two, the oxygen and the hydrogen. And if you start to detect some issue with it, you would shut down both sides and then just have the oxygen and the hydrogen in their separate canisters and not let them react. Next question, what is the life expectancy of fuel cells, and will there be more economic options to use in cars? Economic options to use in cars. Life expectancy of fuel cells, I don't know off the top of my head. I think the car in the background here has a life expectancy of 7 or 8 years. I'm not sure about that. You're going to have to check that with people who might know more about the life expectancy of the different fuel cell cars, because different companies are going to say different things, right? The companies that sell them are going to claim a different life expectancy, and there are different issues going on. Life expectancy at the moment is a bit low. As I said, one of the reasons we use graphene is because it lasts a lot longer, and that's one of the main degradation routes of the fuel cells. It's the carbon support deteriorating. So in the future, hopefully, maybe my work, maybe somebody else's work will help improve the life expectancy of the fuel cell cars. More economical options. Well, you've got to balance economy with renewable and energy systems. And to be honest, running cars, at the moment, we kind of have two main options, which is batteries and fuel cells. Batteries at the moment require lithium and cobalt, both of which are very rare materials. Cobalt in particular is interesting because a lot of the cobalt mined that goes into your smartphones is actually mined by child slave labor in the Congo, so Democratic Republic of Congo. So that's not good. So there are issues with the life expectancy and the issues of economic options, but this shouldn't be considered comparison to petrol cars. We should be saying we are getting rid of petrol cars in 10 to 20 years. This is our only option. We have to deal with the prices, and car companies and scientists will innovate after that and make them cheaper, and they will get cheaper. Sorry, that long question. Next one, which would better, fuel cells and automotors or the standalone energy storage system? I personally think that we don't know how the kind of energy landscape will look in the future. We don't know if battery technology will suddenly stop using lithium and start using sodium. And if you use sodium, it will be a lot cheaper. So then most personal cars will be made out of sodium-ion batteries. Maybe. Maybe sodium-ion batteries don't work. Maybe everything has to be run on fuel cells. We don't really know at this point. There's a lot of science that's been done that we don't know how it's going to end up. So we're probably thinking that a combination of battery cars and fuel cell cars will exist. Fuel cells cars will mostly be more heavy goods vehicles, more industrial applications. So your personal city car will most definitely be a battery, but maybe specialized long range cars or long distance cars or heavy cars or trucks will be fuel cells. Standalone energy systems, again, batteries and fuel cells are very different and will have their own different benefits and negatives, etc. But both will probably be used in different applications. And they'll both all be used in every application, no doubt. Next question. Is electricity taken from electrical current or from reaction of the energy of the reaction? The energy of the reaction is harnessed as an electrical current, is the best way of describing it. So the reaction has energy, but what you're doing is you're doing that reaction in a controlled way that generates electrons, and you're taking the energy from the electron, from the electrical current. So kind of both. So, okay, next question. How does it solve problems like high explosives? It's very dangerous to drive around cars with high explosive stuff. Well, your petrol car is full of highly explosive stuff. Your battery car is full of highly explosive stuff. Every car, as I said before, every car is a way of storing energy. Energy is intrinsically unstable. If you damage a battery or you damage a petrol car in the wrong way, it will explode. Same with fuel cell cars. Relative safety stuff, to be honest, I am not an expert on relative industrial safety of the things. In my opinion, they're all pretty similar. They're all pretty dangerous. You saw what happened if you put a nail through a battery in that video earlier. It's going to explode. In a Tesla car, you have a few thousand of those batteries. And as soon as the one explodes, all the others are going to explode. It's not going to be good, right? Like any technology, any system that uses energy to power a car to move around, and you're going to have a decent range on it, is going to be potentially explosive. We just have to be careful and have safety systems in place, like I say, there's big hydrogen storage tanks, break-off switches to make sure the gas doesn't flow if there is damage to the fuel cell, stuff like that. So that is something that's going to need to happen, but it's a fake case of all cars. Next question. As the reaction produces water, how do we manage the water produced by the fuel cell, or if we're doing a recirculation problems? Very good question. I alluded to this a little bit earlier. Water generation of fuel cell is kind of required, but also too much of it is bad. It's a bit complicated without going into a bit more, but effectively, those diagrams I showed you earlier were a bit simplified. That H plus ions, those protons, they could transport across a membrane and via something called an ionomer. This ionomer needs water to transport them. The conductivity of those H pluses are dependent on water. So you need water in the catalyst layer for fuel cells to function. So that water generated in the catalyst layer is actually beneficial to the fuel cell. Problem is, if you generate too much, it slows down the oxygen transport. So you've got all these different interconnecting things. It's a bit, you can read more about it now. I will have to have a whole different presentation to explain that. So we're not going to go into it now. But too little is bad. Too much water is also bad. So we try to manage the in-between, and we manage it through how much the temperature of the fuel cell, how much gas we're putting through, because more flow of gas will take away more water, but also the structure of the fuel cell. We can structure in a way to get rid of water easier or keep water in. This is some of the control we have. So it is a big issue. That is a lot of research is on that as well. Next question. What are the major potential applications of fuel cells other than cars? I always like to go with cars because people can understand cars very easily. It's a big thing. One of the main one I think will be the energy storage for the industrial grids and the industrial power grids. So you have stuff like, you need to regenerate the renewable energy and you need to store it somewhere. So you can store it as hydrogen gas. Hydrogen gas is very, very stable. You have it in a big old canister somewhere underground or in air or something. As long as it's safe and a big old steel, you'll be fine. I can store for years and years and years, and there's no risk of you losing charge as you would do batteries and stuff like that. And then you use it when you need to. So I think the energy storage, temporary energy storage for renewable power is the best way it's going to work. It's a closed system. It's very well designed. That's what my feeling. Next question. Is it possible using generated liquid to cool the whole system? Yes. The larger fuel cell stacks need cooling and generally use cooling water. So yeah, you're entirely right. That's what happens in the larger fuel cell systems. Okay, so we've got a question. Can you explain the flow of electrons in the fuel cell? So your electrons are, so I don't have a diagram to describe that, so it's a little bit difficult, but your electrons come through either side. You have a fuel cell stack as a whole system. It's not just this tiny catalyst, it's a whole system. And your electrons will start on one side of the system and transport through a series of electron conducting layers. You have these different layers. And eventually, as it passes through from the outer layers to the inner ones, it will get through to the catalyst layer, the one we're talking about. And so from the catalyst layer, it will have to transfer around back to where it didn't come in. It started the catalyst. The electron started on the anode, so it started on the hydrogen being split into the H plus and the electrons. It would go back outside the, away from the membrane, away from the catalyst layer, from where the gas came in, just through connecting through various conductive things like carbon and steel. And it will transport through that, through an internal current collecting system that will collect the current, and it will then be used to generate power. And then after it generates power, the electron will come transport to the other side of the fuel cell and come to the other catalyst layer at the cathode, and then interact with the oxygen and the H plus on that side, forming the water. So it has basically, those two catalyst layers look like they're very similar on the previous bit. In fact, I'll just go back. This one. Those two catalyst layers, this one and here, look like they're very similar. This external circuit is huge. This electron doesn't go through this like here. It goes all the way back, out, round, and then back in somewhere this way. It has to go all the way around the system because that electron has to go and generate power. And so turn a motor or whatever. So it has to go all the way out through the system. And it's just that everything from this catalyst layer that way, everything from this catalyst layer that way is electrically conductive. This middle layer definitely has to not be electrically conductive, because this is electrically conductive, the whole thing doesn't work. This has to be insulating. So it forces the electrons to go all the way around. Okay, so thank you for the lecture and your time. Can we contact the professors or research associates at UCL through email? Do we have to apply to UCL Pro to contact them? You can. You don't have to reply for. You don't have to apply to contact them. You can just email people. Mostly, if you email a professor, they won't reply because they're way too busy. You can email me. I'll probably reply. Or Mark, who does the outreach stuff, organizing this and the marketing stuff. He will probably reply. We could probably put that, my email address and maybe his, in the comments at some point. Hopefully Mark can do that, who's listening in. So feel free to contact me if you've got any questions. I'm happy to reply. But professors generally don't reply. Sorry. They don't reply to me either. So. Next one. Could water settle in between the layers of graphene and result in reduced efficiency over time? Yes. So this kind of builds on what we said before. Water is generated in the fuel cell. Too much water can be problematic because it stops the oxygen transport. It stops the transport of this. Yeah. It stops the transport of the oxygen. But you need some water because you need water. Water helps transport the protons, the H plus. So we need a balance of it, and it might become trapped, but hopefully between the graphene layers, you won't have an excess buildup of water. And if you do, then that's something you can tune out by changing the properties of the graphene. You can add functional group to the surface, which changes how the water sticks to the graphene. You can add in different materials, some which are hydrophobic or hydrophilic, that changes where the water settles. So this is what I mean about nano-engineering is we're constructing these particular layers for particular purposes on the microns to nanometer scale. So you're right, it can do, and it's something we need to control. Next question. The membranes of fuel cells are made of polymers, and polymers do not work under high temperatures. How are we dealing with problems such as overheating for dealing with a vehicle? So depending on your polymer type, so what this question is talking about is this thing in the middle, which is labeled here as an electrolyte. This grey line here in the middle electrolyte is a polymer. These H pluses are transported from polymers, typically naphthalene. Now it isn't always. There are other types of polymers. Naphthalene is the widest used and one of the commercially most available. And so you need these to transport the protons. Polymers typically can melt at high temperatures. It's a thing that can happen. Every polymer is different. Everything has a different melting point or have a different glass transition temperature under heating, different proton conductivity. So the polymers that we use for this middle layer to conduct the protons are, and act as a membrane, act as an insulating membrane, are designed to operate at the temperature the fuel cell runs. Now, so that's 80 degrees. Any higher than 80 degrees, you start to have a breakdown of the polymer, and if you break down your polymer, the entire system collapses and it's going to not work. So you don't want that. So you typically set your temperature range to be within your polymer lifespan. There are different polymers, so you can go high temperature if you get polymers, but there are some polymers aren't as good as others, and it's a whole mess. It is being worked on what's the most optimized route. And overheating of the vehicle, generally water cooling is what happens. You have coolant pipes that go in and directly cool the fuel cells when they're in the car. Next question. After the electrolyte, the H plus and the oxygens are no longer part of the electrical. Now, how do you make sure the energy is released from the production of water? The energy is released from the transport of the electrons, not when the electrons reach the water. It is the when the hydrogen reacts on the left-hand side, it generates an electron. When the water and the oxygen connects on this one here, there's a potential difference between the two. So there's a potential for the electron to go round, and there's a certain number of electrons going round, so generating current. If you put this through a circuit, you can use this potential and current to generate, generate power, because you have a current, you have voltage, you have power. And when it gets to the other side, it's simply completing its route. The power isn't being generated here. The power is being generated here on the transport between the electrons from one side to the other side. But you often do get waste heat if you're doing an inefficient process. You can't harness 100, you can't get 100% efficiency, so you get this waste heat generation, and that can cause problems at the site of the oxygen, on the site where the electrons meet the oxygen. That can cause problems. Typical vehicles have modular power packs, so if some of the batteries go wrong, the whole battery does not have to be replaced. This is the same for hydrogen fuel stacks in these cars. You can build modular fuel cell systems. Yeah, there's no reason you can't. Generally, they're all interconnected in the same way and fed by the same power. So if one were to go wrong, as long as the car was designed in a way to have a shut-off valve, so the reactants didn't go into the broken one, you should be able to keep on going. It really, they can be designed in that way. It depends on the car and the car manufacturer, how they want to build it. That's kind of the answer to that question. They can be done. It really depends if someone wants to do it that way. And I think they are done that way. Yeah. Cool. That's all the questions. Thank you guys very much for listening. Hope you got something out of it. Do we have we sent my email address around? More. Okay, so yep, there we go. There's my email address. Cool. That's everything. So thank you very much, guys. Any final questions? If not, then see you. Have a good summer, and good luck with whatever happens with your exams and stuff. I have no idea. Good luck. Have a great day.